Well, good morning, everyone. I can go through the quiz and I'll get started this week. It's going to be Alex and myself going through everything. So I'll start with number one on the quiz. HMA pavements are designed very carefully, so they don't need to be tested after production. If you guessed false for that, you'd have been correctly. Testing is a huge part of what we do. Um, everything from the design phase is critical, but the reality is the production and carry out phase of everything is just as critical. Number two, specific gravity is the ratio of the density of HMA material to the density of water. If you answered true for that, you'd be correct. Okay? So anytime you see a specific gravity, that's how many times denser that material is than water. Number three, maximum specific gravity measures the specific gravity of the HMA as if it had no air voids. And that is correct. That's exactly what it's doing. And what that does is that gives us a target value both in the lab as well as a target value in the field when we are trying to achieve density and air void content. Right. Let's see, Alex, if you could scroll. There we go. Okay. Number four, maximum specific gravity, GMM, and bulk specific gravity, GMB, can be converted to density. Okay. If you answered true on both of those, you'd be correct. GMM and GMB are specific gravities that are unitless ratios. So anytime you multiply them by the density of water in any units, whether it's pounds per cubic foot or grams per cubic centimeter, you are going to end up with units of density. So if you guessed true on that, you'd be correct. Okay. Number five, the specific gravity of water is how many pounds per cubic feet? In the HMA world, this is something we use all the time. And so if you guessed 62.4 pounds per cubic foot, you'd be correct. So in relation to the specific gravity question above, if you multiplied any specific gravity by 62.4, you would end up with units of density in pounds per cubic foot. Okay. Let's see. Number six, the GMM for a collected sample is 2.560. So the density is how many pounds per cubic foot? Do this. So I'm going to take 1 second here and actually calculate it. I think I know the answer, but I don't want to be incorrect here. Stand by. Oh. Alex brought up a screen. It's good. All right. So we take 2.560, multiply it by 62.4. That should give you 159.7. And that's pounds per cubic foot. That's how we convert specific gravity to density. For the next one, we have a GMB, again, a bulk specific gravity of 2.389. So 2.389 on the GMB computation, if you multiply that by 62.4, that should give you 149.07, which rounds to 149.1 pounds per cubic foot. And just an FYI, with both of those densities, those are numbers that don't seem like red flags at all to me. Okay, those are very, very reasonable numbers. And so, if you saw those, you could have confidence that your computations were correct. Number eight, density can be measured on laboratory compacted specimens, but not cores cut from the roadway. That would be a big problem if that were true. We'd have to figure out a lot of other ways to do things, especially here in Connecticut, because cutting cores from the roadway and then measuring the density of them is how we determine payment on our paving projects. Okay? So that's going to be false. Number nine, the compacted density of a specimen is 144.0 pounds per cubic foot, and the maximum density is 150.0. So the percent compaction is what? And all we would have to do there is to divide our compacted specimen density, okay, of 144 by the maximum of 150, and then multiply it by 100. Okay. And so in that case, if you do that, you end up with a density of 96%. Right? 96% density. which also translates, by the way, to 4% air voids, because if you add your air voids to your percent density, you get 100. Okay, and that's always true. All right. Let's see, number 10, the percent density is 93.5. Okay. So the percent air voids is what? And again, if we just take 100 and subtract our percent density from it, we will end up with our air voids. So in this case, 93.5 subtracted from 100 is 6.5%. So we have 6.5% air voids there. Okay. Before we move off of that, does anybody have any questions on the quiz material? Okay. If you do, I suppose throw it in the chat. I'm going to bring my chat up just to make sure.
It's been a busy morning.
That's all right. I completely understand. Had a lot of those lately.
Yep.
Okay, so what we're going to do is we are going to talk about asphalt content. And we'll start with the beginning slides here, just kind of an intro. So this is session number 6. We're going to talk about a few different tasks that as QC folks, you are definitely going to see a lot of this stuff. The stuff we're going to talk about specifically today is measuring the liquid asphalt content of a produced mixture. All right, with both the ignition oven, and then we're going to talk briefly about what is known as a solvent extraction. We're going to look at measuring the thickness of a compacted specimen, whether it's a cut core or if it is a specimen that we developed and compacted in the laboratory. Now we're going to look at something called drain down. All right, if we have a special provision mix, or if there's a specialty mix that has specifically a large asphalt binder content or a large asphalt binder film thickness. And when I say large, I mean larger than normal. We could be concerned about drain down. And then finally, we're going to look at what's called moisture-induced damage of HMA, where we take a look at the potential for the liquid asphalt to literally strip from the aggregates when it's in place. All right, and there's actually a laboratory simulation and test method that we go through to look at that. So these are the different things that we're going to cover today. Okay, that's good, Alex. All right, so why asphalt content? We know from previous classes that the roadway, if you look at the pavement specifically, it is made up of roughly, these are rough numbers for dense graded pavements, 95% sand and rocks, and the other 5% is the glue that holds it together, and that's the liquid asphalt binder content. And that's a critical number, okay? If we are a little bit too high on asphalt, we can run into permanent deformation potential. So things such as rutting and shoving and also bleeding of the liquid binder, especially on a hot day. And if we have asphalt contents that are too low, okay, then we have to worry about raveling of the pavement. We might not get complete coating of all of the aggregates at the plant and so forth. And so there's kind of a critical threshold that we don't want to be above and below. All right, we want to really meet what our design asphalt contents are. And so we want to make sure that we have enough asphalt to remain durable, but not so much asphalt that we lose durability on the other end as far as permanent deformation goes. Okay, and just an FYI, when we mention permanent deformation, I find myself saying this a lot and not explaining it. So permanent deformation, I'm generally talking about rutting, right? When the pavement actually ruts, okay, and the asphalt mixture actually squeezes out in the wheel paths and it creates a rut. We're generally talking about that with respect to permanent deformation, that cracking. Okay, Alex, that's good. All right, so how do we measure it? When we batch things out and we put a mixture together, we simply do it by weight. We can actually weigh it on a scale and then add it to our mixture in the laboratory. But that's not how things are done at a plant. And if we want to keep the plant running correctly and tell what the output is, we need tools to be able to tell us what the asphalt content of that produced mixture is. And so what you see in this image is what's called an asphalt ignition oven. Okay, hot mix asphalt ignition oven, and this oven heats up to 1,000 degrees Fahrenheit. And we literally burn the asphalt off of the aggregates. So we get a weight of our mixture. Okay? then we apply all this heat inside this ignition oven. It burns the asphalt off until it reaches what's called a constant mass. We'll talk about that in just a couple minutes. And then we weigh the remaining aggregates. And the difference between your starting weight of your mixture and the remaining weight of the aggregates that are left in the baskets, okay, that is the weight of the liquid binder that was burned off. And we know how to do percentages. If we take the weight that was lost, that is liquid binder, and divide it by the original weight of the mix and multiply it by 100, we can come up with an asphalt binder content. There's a couple more nuts and bolts to this. We'll talk about what those are, but that's basically the gist or the scope, if you will, of what we're looking at here. Okay. And so what you see in this image are a set of baskets. Okay, that is a number 8 or 2.3 millimeter opening basket. There's actually 2 of them that are set on a tray. And what we do is we weigh those baskets and then we weigh our mixture into those. And then those baskets that are holding the mixture go into the ignition chamber on the ignition oven. And that's where everything happens. It happens inside of those baskets in the chamber. And you can see those baskets inserted into that chamber. And the way that this works first is we have to heat the oven up. The oven can take quite a while because that's a significant amount of heat. 538 C or 1,000 degrees Fahrenheit is very, very hot. And so it takes some time to heat these ovens up to temperature. But nonetheless, that's what you see there on this ignition oven. And underneath the door, so you go back one slide, Alex. Underneath the door, what you're looking at is an onboard computer. We can program all kinds of stuff for this ignition oven. We can put in correction factors, which I'll discuss in just a couple minutes. We can turn the oven on. We can set the oven to come on at a certain time. We can program a bunch of different features. We can input starting weights. We can change things. We can print previous tests. There's a number of different things that these are capable of doing. All right. And so what you see here, this is looking inside the ignition chamber itself. It's thermally isolated. What you're looking at, those white walls, both in the back and on the top and on the sides. That's the thermal isolation. Those are insulated walls. And on the bottom, what you see is a platform. And that platform goes down to a scale that sets on top of the computer in the bottom of this machine. And that's also has to be thermally isolated, obviously, because if it wasn't, we would simply burn the whole unit up. And we've got to make sure that doesn't happen. And so that is a scale. And this oven can actually weigh the material as it's losing liquid asphalt. Okay, the mass goes down, 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 down until finally it's all burned away. And then we're left with just the weight of the aggregates. And the oven can actually sense when it's done burning, because when it stops losing weight, it knows that there's no more asphalt left to burn off. And we call that condition constant mass. When it stops losing weight, we know that all the liquid asphalt binder is gone. And so what do we do? Now we've got these baskets, okay, that have all of these very extremely hot aggregates, stone and sand inside them with the asphalt all burned off of them. We use a pair of tongs and we use, thermal gloves like welding gloves and a face shield and so forth. We have to use lots of personal protective equipment when we do this because of the extreme amount of heat. Okay. And so we remove those baskets and we set them on a countertop. Now, it's important to keep in mind what that countertop is made of, because again, you're putting something that is 1,000 degrees on top of it. And so a wooden or plastic countertop really would not be ideal here because you would damage it. Especially plastic, you could cause some serious problems with a plastic countertop. Okay. Alex, that's good. And so another element with that is we have these barriers. Okay, the danger, hot, yeah, absolutely. If somebody were to walk by in your laboratory or in our laboratory or whatever and just brush an elbow on those hot baskets, they're going to get burned very, very badly. That's an extremely hot temperature. That's not your standard oven temperature. You know, if you're baking a potato or something like that, it's quite a bit hotter than that. And so we need to again exercise plenty of safety measures, using again gloves, face shield. Tongs to handle the baskets, and then to protect people from not touching those baskets as they're cooling down once they've been removed from the ignition oven. And so after about a half hour, okay, you've got about a half hour or half hour to 40 minutes, depending on a number of different things, specifically the mix. What you're left with is these baskets can actually be handled now. And so we can take these baskets and we can externally weigh them if we want to check our numbers versus the numbers that are output on the ticket, which I'll talk about in a minute. But what you see here are the burned aggregates. Those used to be part of the asphalt mixture, but then they were put into the ignition oven. The asphalt was burned off, and now we're back to just sand and rocks. So this whole thing is like a deconstruction process. We're trying to take the mix apart in order to determine what the contents and what the mix constituents are. So we can run a sieve analysis that we talked about in previous classes to figure out what the gradation is of that mix to check what it is versus what's called the job mix formula, where we have to meet certain requirements with those gradations. Right? And another thing that computer does that I didn't mention earlier, I guess I did mention it maybe, is it prints a ticket. And the ticket tells you all kinds of pertinent information with respect to what happened with that mix over the course of the burn and what the final asphalt content is. So up top, I'll start right at the top. It says elapsed time. For that specific burn, it took 55 minutes in order to burn the asphalt off and get to a constant mass. The initial sample weight was 1,699 grams, and it lost 93.0 grams. And so that translates to a percentage of 5.47. Now, something that I didn't mention earlier are we have to compensate for a few different things. There's what's called a mix correction, and then there's also a temperature correction. So I'll start with the temperature correction. This is something that the oven generates. If you think about the way that these ovens work, the temperature has an awful lot of influence on exactly what that weight is. And so these computers that are built in can compensate for the effective temperature on what that weight loss actually is. And so that 0.18% was actually generated by the oven. The next thing down, you'll see it says calibration factor, that C-A-L-I-B. That is short for calibration. Each individual mixture has to have what's called a calibration factor. And we run this beforehand. We determine what these mixtures are beforehand during production because we have to know about how much material we're not accounting for that may have gone up the stack, the particulate matter that may have been lost through the exhaust on the ignition oven, or any number of combinations of other things that people, wonder what exactly is going on here. But nonetheless, that calibration factor is something that we determined previously, and then we enter it into the oven prior to running our mix. In this case, we had that calibration factor set to 0 because we weren't running a mix that we had a calibration factor for. But during production, there's always a calibration factor when we're measuring the AC content, okay? And so then you have the bitumen ratio, and then the calibrated asphalt content down below is simply all of those numbers with all of the calibration factors and correction factors applied. So in this case, we ended up with a calibrated asphalt content after everything was all said and done of 5.30%. Okay. Okay. All right. So that is extraction for asphalt content via ignition oven. There's another method that is an older method. Before ignition ovens ever came out, what we used to do was we'd use a solvent. Some of these solvents were pretty nasty, but it had to be something that asphalt was actually soluble in. So this test actually revolved around and was designed around the use of a solvent called trichloroethylene. And so what we would do is we would soak the mixture in this trichloroethylene, and that solvent would dissolve the asphalt. And then we'd use a centrifuge, which is what's shown in this picture right here, to spin that liquid off. And we would repeat that process until we were left with just the clean aggregates. And so in that case, instead of burning the asphalt off, we were literally washing it off with a solvent that, something that liquid binder would be soluble in. This is not something that happens very often at the lab, but when we do these at the CAP lab, if you ever come out and visit us, sometimes we do these because we want to save the liquid binder. We want to recover the liquid binder for further testing. Other times it can be done if we're dealing with recycled materials. We might want to use a solvent extraction. And there are states out there, believe it or not, the state of New Hampshire comes to mind, that require this method for asphalt determination. You won't find ignition ovens. If you get up into the state of New Hampshire, what you'll see are centrifuges in smoke hoods that deal with solvent extractions. And so there's a couple different ways to do this. But again, just the gist of it, the major point to make here is that with a solvent extraction, instead of burning the asphalt off, we're washing it off. Okay. And so, yeah, you're not going to see this very much in Connecticut anymore, unless there's something special going on, like you're dealing with recycled products or you're trying to recover the liquid binder. But for standard PVs or asphalt contents, which are also known as PVs, you're going to be seeing ignition ovens are going to be the the lion's share of the way that this is done is going to be through ignition ovens. Okay. Okay, so moving on from asphalt contents, make sure I'm taking up too much time here. We we're going to move on to measuring thickness. Okay, we have to be able to measure the thickness of either cut cores, compacted lab specimens, and in particularly, also in addition to that, I should say, performance test specimens that we might run in the laboratory. And there's all kinds of reasons to be able to run thickness. Excuse me. Is everybody? Either we got a big gust of wind or we just had an earthquake in Canaan. Can you still hear me? All right.
I can hear you.
I think we're getting it here too in Rhode Island.
You felt that?
My whole house is shaking right now.
My whole shop just literally shook.
It's still shaking here.
Really? Alex,
Like
did you get
earthquake?
That's
No.
pretty awesome. That's the first earthquake I've ever felt.
I have never experienced that in my life. That was odd.
Wow.
What's weird is we didn't have it here, considering you felt it in Rhode Island.
Yeah, it just stopped.
And I'm way out towards the New York border from where you guys are.
To see where it
Funky.
started.
Wow. Yeah, I'm sure we'll see it on the news.
Yeah.
I'm gonna I think I'll keep going just in case we lose power or anything bad happens, we can get through this. So in any case, measuring compacted specimens is necessary to ensure that we have enough material for whatever it is we're doing, and also to meet different specification requirements if we are running, let's say, performance tests or anything like that. Okay, and we can calculate volumes and everything based on those thicknesses as well. Okay, that's good, Alex. And so again, we can measure thickness on cut cores, or we can measure thickness of compacted specimens on lab compacted specimens. And that's what you see in the right-hand image is a lab compacted specimen, which Alex and Jim went through the gyratory compactors in previous class, right? We could do them on the cut cores as well. And the way that this is done, that's good, Alex, typically and most commonly is we divide these compacted specimens into quarters. Okay. And so we have a quarter. In each quarter, we're going to make a thickness measurement. And we're at the end of it, we have those 4 thickness measurements, and we simply average them together, and we come up with an average specimen thickness. Okay. And so there's a tolerant, or I shouldn't say a tolerance, there's a it's a word I'm looking for. We have to be as specific as losing words here. It's my first
the symptom of the earthquake.
My goodness, yeah. I guess maybe I'm having tremors. And so in any case, this is how level of accuracy is the term I was looking for. We have to measure these at least to the nearest 16th of an inch, or also to the nearest 10th of a centimeter or millimeter. Good, Alex. And so what they're showing you here, what you see in this image on the left-hand side is a set of calipers. These are digital calipers. And so we take a measurement in each of the quarters and we write down whatever that reported thickness is. Okay, in this case, what you read on there is 56.11 millimeters. We write that down. We do that 3 more times for the other 3 quadrants and average those values together. You don't have to use a set of calipers. You can also use a ruler, a metal tape, or a measurement jig of some sort, as long as it's something that's calibrated and it's accurate to the nearest 16th of an inch or 10th of a centimeter. Okay. And so here's just an example taking 4 measurements of, let's say, a cut core. If you end up with 5, 5.7, 5.1, and 5.3, and we do a simple average on that, if you add those numbers together and then divide by 4, you'll end up with the average thickness that then could be reported along with that specimen. And so in this case, it would be 5.3 centimeters. Right? And that would round to 5.3. Okay. And again, we have to be accurate to the nearest 10th of a centimeter. And so that's why we rounded and reported it to where we did. Okay.
All right. So another one of the characteristics we're going to be testing during a design, as well as periodically during production of certain pavements, especially specialty pavements, which I'll touch on later on, is drain down. And this is literally when there's so much asphalt or it's an asphalt-rich design that we're concerned that it's going to run off of the particles, like if you put too much paint on something and it runs. So, like I mentioned, it's typically only measured on specialty mixes. And what I mean by that is when you've got something that's not dense graded, so the particle size being uniform, that's considered a dense graded mix. When we have large stone all the way down through small. If we have something that's gap graded or open graded, meaning we have a certain amount of large, there's nothing in the middle, and then only a little bit of fines, or there's only large and nothing else. You'd see that for something called like porous pavement, which we might have touched on. If not, we'll probably go through it a little later on. There's also mixes called open graded friction coarse or Nova chip. Those are both considered gap graded. There's also a new mix we're trialing in Connecticut this year known as SMA, stone matrix asphalt. That's also considered a gap graded mix. And these have a higher asphalt content because there's less stone in them. And we put less stone in for two reasons, actually, or we put more asphalt in for two reasons. So when we have these open graded or gap graded mixes, we not only have less particles to coat with the asphalt, but we need that asphalt to help hold it together. Usually a dense graded mix has more stone on stone contact that's locking. It's called particle interlock of the stone matrix. But anyway, we need to monitor this and make sure they're designed properly. So here's a really extreme example. Actually, I don't even know if that's asphalt in that picture. I guess it is, right? Drain down refers to the liquid coming off of the mix, and this happens most especially during production in a silo and during transit in a truck. You can think of the truck trip as being the worst because there's vibration. There's actually a photo in some uh, educational presentations we have where you actually see a pond of asphalt at the surface of a truck's load because the asphalt vibrated so much it actually wicked its way away from all of the stone. So that's an extreme drain down example. The test itself is pretty straightforward. We've got these mesh baskets, right? Lots of mesh today between the ignition oven and the drain down test. So here we've got 1/4 inch mesh baskets. We're going to fabricate our mix, or it could be plant produced and we sampled it. Either way, most of the time this is done during the design process, so it's a lab manufactured. We need an empty weight of these baskets and the pan. Then we're going to put our material in that basket in the pan, weigh it all together, and then load the basket into an oven for an hour or 60 minutes at that production temperature. Now, the plant production temperature, as a reminder, comes from what's known as the bill of lading, which is just paperwork from the binder producer. So the people who make the liquid asphalt, remember with that whole PG grading system regarding viscosity or the stiffness of the fluid, they're going to tell us at this temperature is how you're going to mix it. So it's not a temperature that you're guessing or that a specific plant uses all the time. It actually pertains to the binder itself. So we're going to spend 60 minutes at that temperature, and then we're going to measure how much material is left in this pan. And you can see this is actually a pretty good example of drain down where there's liquid asphalt left behind. There's a minimum amount that's acceptable, and the weight of the material in the pan is divided by the initial weight of the sample and expressed as a percent. There's a lot of percents we deal with. So, that's something mathematically like doing gradations, right? Doing percent compaction and percent density. We're going to see those types of calculations over and over again, but here's another example where it's the same type of percent. So in this case, we've got an initial sample of 1250.0 grams. And then after 60 minutes, we have 6.2 grams left behind. Oh, and then here is a typo. That should say 6.2 grams. I apologize. I did not correct that. That was on me this morning. Too many things going on. So if we do our 6.2 grams divided by 1250, oh, the hotkey does not work. Divided by 1250, we're getting 0.49 or 4.96 if we multiply that by 100. 0.496. So in the case of the 3.7, this example is correct down here as well. You get 0.3%. And every specification is going to tell you a certain amount that's acceptable. Now, moisture-induced damage of pavements, otherwise known as stripping, is a really important characteristic. So similarly to rutting, moisture damage is something that I call a catastrophic failure. It happens prematurely, like with rutting, it will happen within the first 3 to 5 years. Same thing goes for stripping. And what happens here is there's all sorts of inter sub molecular forces. That's the word I'm looking for. Friday mornings, right? It's tough. We've got a lot of molecular forces acting on the asphalt and the aggregate and water. So you'll probably recall from science class that water has some sort of polarity associated with it, right? It's different than a normal molecule because there's some sort of magnetism in there. Not necessarily magnetism, but subatomic, you know, electrical charges. And the same thing happens in asphalt and actually in rocks in aggregate. And depending on your aggregate source and your binder source, you might have this interaction where water can actually peel it away, peel the asphalt away from the aggregate. So it takes both things, right? It's not necessarily one aggregate all the time, and it's not necessarily one binder all the time. A good example of this, and actually an example most of us live through in the Northeast is people with radon fans in their basements, right? This is an example of aggregate that is reactive. It's changing its properties as we're exposing it to our environment, right? So we're talking about bedrock that was buried for a long time. We bring it up to the surface and we're going to build with it or do something in and around it. That's going to affect these unstable aggregate. And it's not unstable in the sense that it's going to fall apart. What I'm talking about is chemically, where it's actually going to change. So the long story short is, sorry about that, we want to make sure that the asphalt and the aggregate don't peel apart from each other. And the way we're going to do that is with a test known as AASHTO T283 or the TSR, tensile strength ratio test. In Connecticut, as in all of New England and the Northeast in general, we're what's considered a wet freeze climate for transportation infrastructure. It's really, really harmful to infrastructure, as you've noted, right? A lot of people like to complain about our roads. They deteriorate much faster here than they do in other parts of the country. If you have a dry freeze, like in the Northwest, or if you're in the South and you don't have any freezing conditions at all, infrastructure tends to last a lot longer. So this stripping condition is most prevalent here in the Northeast. The way we're going to do this is, like I said, the TSR tensile strength ratio test. So we're going to take 6 gyratory specimens. We're going to keep 3 as a control. So we do nothing to those 3. We're going to take the remaining 3 and we do what's considered a torture test or a laboratory simulation of damage. What we need to do is saturate them, freeze them, soak them in a hot water bath, and then we crush them. And we're going to compare the 2 numbers, the control set versus the one we tortured, and see how different they are. If there's too much difference, that's a sign that stripping is going to occur. So this loading configuration, where we actually set it on its side, and you can see in this picture here too, this is a good table trivia for you tonight. This is known as an indirect tensile configuration. And the reason we'll do this, right, you might think similarly to concrete, well, why don't we just put it on its top and crush it that way? The reason being is when you do what's known as a uniaxial compression, I know I'm throwing a lot of engineering terms here, but hey, what the heck, it's Friday. When you when you crush a concrete cylinder, which looks more like this, you're only testing for compression. Now, asphalt experiences a lot of tension, tensile forces, and actually those are what's more likely to cause its failure compared to compression. However, in this configuration where you stand it on its side, we're actually testing both failure criteria at once inside the specimen. If you go deeper into engineering, there's something called mechanics of materials where you actually would be able to analyze what's happening inside this specimen as you fracture it, but it's actually going to fail in a crack straight up this way because of tensile strain concentrations in the specimen. A little extra information for you there, but the key is we're going to test the control versus the damaged ones and see the difference. Is this a video? I think it might be. I usually have 2 screens, so I'm a little technologically struggling here. Yeah, there we go. Nice. This is at our lab. Old setup here in room 100. So that head is moving at 50 millimeters per minute or 2 inches per minute. So it's not a very exciting failure in that you don't see much happening. So what we're seeing at the end screen here is our peak load of 6,837 pounds. Not a huge amount of force required to damage that specimen. It's a pretty small specimen though, right? When we have asphalt in place, it's miles long, but the thickness is going to be about the same. These samples tend to be 95 millimeters thick, unless you're doing ASTM testing. So, whoops, jumped ahead too many. So after we crush them, we're actually going to inspect them as well. This is part of the test. We want to look for aggregate here that's sheared, where the aggregate failed before the asphalt, or aggregate where we see stripping, where the liquid asphalt has peeled away from the aggregate itself. And then we're going to look at the control. We're going to look at the condition specimens, and we're probably going to need time for it to dry. So here's a close-up that's showing some extreme stripping. And you can see here, if there was cracked aggregate that severed during the test, you'd see white powder in the vicinity of those. You don't see a lot of that happening here. So you see aggregate exposed. And in these cases, you can tell it's kind of weathered and it's not a new face that we've fractured. It's aggregate where the asphalt has literally been peeled away from it. I think I went a little fast on that. But we could actually have a quick look at quiz number 6, give everyone a head start on that. Do people have any questions about these tests? The tests that Scott and I went through today are really like run-of-the-mill tests in a sense. They're more advanced performance tests that are coming to labs across the state and across the country, but the tests we've described today, and actually, including bulks and T209, that stuff gets run all the time. So having familiarity with this stuff is important. The other thing worth mentioning about moisture-induced damage or stripping is because it's a chemical phenomenon that's causing this, they can put an additive into the binder known as an anti-strip, and it solves the problem. So as long as you know you have a stripping potential, it can be mitigated or avoided by adding some of these chemicals. But as someone who produces this, right, as a contractor, you don't necessarily want to spend that money if you don't have to. So there's always this testing going on to make sure they're spending it because they need to, right? You'll take out the anti-strip and test it and see that you still have a stripping problem, and then rerun it with this anti-strip and make sure you're passing these tests. The other funny thing worth mentioning about AASHTO T283 is it's an empirical test, right? So it's kind of similar to what happens in the field, but it's not exactly testing something known as a mechanistic property or a fundamental property of this pavement. So I get a little bit excited about fracture testing. That's one of our areas of expertise at the CAP lab. So I apologize if that got a little technical, but there's a lot that goes into it, right? It's fun because, at face value, what we do at our lab is we weigh rocks and we crush them, but there's actually a whole lot of science that goes into these roads. And I mean, you're definitely getting a flavor for that in this class. But yeah, I guess we'll pull up quiz 6 and we can have a quick look at some of those questions. I know some people get out around 10:50, 10:55, so we have a little bit of time left. Quiz 6. All right, I'm only going to look at half of them, I think. The rest of the quiz you should do on your own. But we can go through this together. Question number 1. As long as the HMA is properly compacted, the asphalt binder content is usually not a concern. So type your answers in or feel free to unmute yourself too if you have a guess. I'm going to give you a minute to answer before Scott or I give you any answers. We wrote the quiz, so we know. the answer. What do people think? True or false? Once we've dialed this in, we don't have to test the binder content.
Are we sharing the answers right now? Because we have an answer.
Oh yeah, please do.
Okay, go ahead, Ty. Go ahead. Now he's shy.
False.
Excellent. Thank you. Yep.
False.
As with almost everything with pavement, it's a dynamic process, and that, one wrong scoop of material into a cold feed could change the output through the paver. So we always want to be testing this to make sure the product is uniform. Really good. Question number 2. Asphalt binder content is used in volumetric determinations along with GMM and GMB. What do people think? True or false?
Got answers here? Can we share?
Yeah.
Okay.
True. True.
Okay.
100%.
That's
So,
smart. Look at that.
Another good dinner table trivia is the term volumetrics, which we use in pavement for describing how we mathematically characterize the mix. And that relationship between specific gravities, binder content, and all the gradations we've been talking about, that's exceptionally important to how we're going to get density and an indicator of the quality and uniformity of the material. So, yep, very good. True. Question number 3, loose mix is placed into blank prior to entry into the ignition oven. And we've got a couple options here. Heat-resistant glass beakers, gyratory molds, metal baskets, or ceramic plates.
We have an answer here?
Shout it out. We'll take them all. Thank you.
C, metal baskets.
Yep. Really funny side note, we'll actually clean our glassware in our ignition oven. So glass beakers, if we pour asphalt into a beaker, we can then clean it by just burning off the asphalt in our ignition oven. But yes, metal baskets, and remember it's a number 8 for the opening on those. You can't overload them, so it's important. That's why you saw the 2 stacks there. We have 2 more questions I'll go through before we let you finish off the rest of the quizzes on your own. Question number 4, the ignition oven uses a built-in blank to determine when the binder is removed and the burn is complete. A, thermometer, B, pycnometer, C, carbon monoxide sensor, or D, scale.
Scale.
Right.
Yep. All the extra credits going to Kim's group today. And then
I got them a lot of snacks this morning, so I think they have extra energy.
Nice. The last question I'll go through before we relieve you for the day is thickness measurements are made in each blank of the compacted specimen. And this is referring to thickness, as mentioned up here. Portion, quarter, third, or half.
Tyler's saying quarter.
That's right.
Sounds good to me.
So proud.
So everyone should get at least a 50 on this week's scale, or this week's quiz.
I'll make sure. We'll check those numbers.
Yep. And as always, if anyone has any questions or thoughts about today's presentation, don't hesitate to reach out to Aaron or to Scott, Jim, and I. But otherwise, thank you all. Have a good weekend.
Thanks, everybody.
Thank you. Have a great weekend too.
Take care.
We will meet. We don't have class next week, but we do have it the following.
Oh, okay.
That's right, spring break, right?
Yep.
That's our spring break is the following Friday. So we're in session on the 12th, but not on the 19th. So we'll just do the, you're gonna record.
Just do the videos, Kim, when it works for you guys.
Okay, sounds good, Erin. Thank you so much.
Thanks, everybody.